We are going to examine the first part of the paper entitled A Model of Time. The focus will be on what we can call hyperverse time. So, what is time? Time is the most common word used in the English language. Whatever time is, life is unimaginable without it. For being so completely integral to existence, no good theory of time exists. The bottom line is we don't know. The situation is so bad there are many physicists who believe that time is imaginary and does not exist. We know some things about time. Time is somehow connected to the expansion of space because it is generally thought that time did not exist before the Big Bang. Time flows in one direction, to the future. This is the one-way arrow of time. Relativity says time can move at different rates for different observers moving relative to one another. And we can ask, is time quantized? That is, does time come in discrete units? A model of time should explain its connection to the expansion of space, the one-way arrow of time, relativity, and it should tell us if time is quantized or not. Our model of time will do these things. From the Hubble constant paper, we saw that the universe is the surface volume of an expanding, hollow, four-dimensional hypersphere we call the hyperverse. This is a representation of the hyperverse. The center is hollow. The surface is three-dimensional, and it is our universe. And it is expanding at twice the speed of light. There are a couple of ideas to address now, the first relating to the structure of the hyperverse surface volume. We are going to make the claim that the hyperverse surface volume is composed of atoms of space as discussed in the first video, the one on the Hubble constant. The atoms of space are miniature 4D vortices, and they spin. The surface volume, which we have been representing as a squiggly line, might be better represented as a series of atoms of space as such, but we're going to keep doing it this way. So how thick is the hyperverse surface volume? We're going to approach this first using an analogy. Let's look at a 3D sphere and its 2D surface area. As shown here, a three-dimensional volume has a two-dimensional surface area. The two-dimensional surface area could be viewed as being flatland. This analogy of flatland is based on Edwin Abbott's 1884 book titled Flatland. A flatlander can see to his sides and front and back. Flatland is not flat to a flatlander. They see depth in every direction they look. But a denizen of flatland cannot look up or down as the third dimension does not exist to them. From our point of view, as residents of the third dimension, flatland is flat. And by analogy, from the point of view of the fourth dimension, our 3D volume would be flat. But not entirely flat. In the geometric mean paper in this series, we calculate the radius of the surface vortices. So there is a fourth dimensional thickness to the hyperverse surface. It is thin, much smaller than the Planck length. The radius of the surface vortices, r sub s, or small radius, is approximately equal to 4 times 10 to the minus 96 meters. We derive that value in the geometric mean paper. Looking again at the hyperverse, we can take the 2c rate of expansion and divide it by the radius of the surface vortices to see how many expansion steps there are per second. We'll divide the 2c radial expansion rate by the small radius, and we find we get 1.5 times 10 to the 104th steps per second. Given that the hyperverse radius is expanding radially at 2c, and that the thickness of the hyperverse surface volume is very thin, we find that we are not long in one spot. How long? The time duration of one radial step is approximately 6.6 times 10 to the minus 105th seconds. We could define that amount of time as a moment. For our purposes, we'll be defining it as the time of one radial frame advance. And this gives us the basis of the quantum of time. It's the time for one radial step. We are zooming into the fourth dimension at twice the speed of light, and we are at a specific place in space-time for about a moment of time of 10 to the minus 105th seconds. Where we were a minute ago is far behind us, more than 22 million miles away. The past is indeed far away. The arrow of time points to the true direction of expansion, radially into the fourth dimension. This is why time only goes one way, forward, in the direction of the radial expansion. This is why time is universal throughout the cosmos, as all of space is expanding. There is no escape from time, no place in the universe where time does not exist, as all points in space are on the surface volume of the expanding hyperverse. And there's no going back or forward in time. The discussion so far has been what we can call hyperverse time. We are made of atoms and experience atomic time and relativity, a topic we will address in Part 2.